The number one thing that everyone was stuck on was redox. So I've just got a few additional things. Redox is something that you're going to be covering in a future lesson. This was from a section in your book, which was after redox reaction. Some people used their initiative and they found the section in 7.2 that gave you directions. But very briefly, reduction is the gain of electrons, and this is what non-metals do. So here is an example, and you can have oxygen reacting with magnesium. So that's magnesium burning in air. Now, we respect the fact that oxygen exists as molecules, so we use a half to put oxygen rather than just say O. So if I just did that, my common sense would say, well, if you're starting with oxygen, start with that, okay? But we don't do that. We have to respect the fact that oxygen is in molecules. So we have to say, right, yeah, we start off with oxygen molecules, but then what we're going to do is we're going to halve the O's because they hang out as O and O, and we're going to halve the numbers, so we've got it down to O. And then for each of those oxygen atoms that are represented in the equation, we are going to add 2 electrons, and those 2 electrons add to the outer shell of this non-metal. 2.26 becomes 2.8, so it's a full outer shell. And then that forms the oxide ion, okay? It might be useful if I just put oxide ion, okay? Non-metals, half of the oxygens in an oxygen molecule, okay? Now this bit over here is a little bit fuzzy. And the reason why it's fuzzy is because to understand that completely, I need to teach you a concept in year 11 called moles, okay? So that is a little bit fuzzy, but do not worry about it. I'm helping you through it. That half oxygen, the most important thing here to understand is that you've got the oxygen atoms gaining electrons. That's the important point that I want to try and put across here. So the oxygen atom, so half the oxygen, so it's like oxygen atom, half the oxygens in an oxygen molecule, okay? The oxygen atom, that is basically your oxygen atom. Okay, adds 2 electrons and it becomes an oxide ion. So that's now a charged particle, okay? So that's called reduction, okay? And if I just highlight that in a color, that's where that bit comes in, all right? And then oxidation, the oxidation part in the name redox, oh, should do that, there we go, that comes there, okay? There we go, bingo. All right, and the oxidation part, the oxidation seems to be easier for people to understand because metals, we represent metals as atoms on their own, and the atom loses 2 electrons to become a positive metal ion. Okay, so I hope that kind of guides you into how to do the redox question, which everyone seemed to be struggling on. Okay, redox is actually it's actually an interesting one. It's a nice topic. It's one of those ones where you kind of like stare at it and you think, oh gosh, I'm going to have to get my head over this at one point. But once you get it, it's a really good cash cow for points and marks in the exam. Once you know it, you just think, oh, easy, let's do that. Okay. All right. So, an ionic equation, right? This is for the process of neutralization, okay? So, if you have an ionic compound dissolved in water, this is hydrochloric acid. It consists of hydrogen ions and chloride ions. Okay, the molecules of water here are just represented by these blue circles. Okay, here's another example over here. This is sodium hydroxide. This is an alkali. You can tell it's an alkali because it has a source of OH minus ions. Those OH minus ions are called hydroxide ions, okay? So I can tell that this is an alkali. I can tell that this is an acid because it's H+, okay? Now, when things are neutralizing, you actually have water being formed as a result of an acid reacting with an alkali. And that's the most familiar neutralization that you are aware of. But there are other ways of neutralizing acids that you have studied too. For example, an acid can react with a metal oxide. And that does also form water, but it's not hydroxide that's combining with the H+. It's the oxide ion that's combining with the H+. But in this lesson, we are looking at neutralization, the neutralization of an acid by an alkali, which is a soluble base. So if you have a soluble base, it's OH minus hydroxide ions that are present. Just to remind you, this is section 11.4. I'm just quickly explaining ionic equations, okay? So the first thing that I would do if I'm tackling ionic equations for acids reacting with alkalis, which have a source of OH minus, is I need to be able to recognize what ions are present, okay? Now, in this first example, on this double page, you can actually see that you've got hydrochloric acid, so it's H+, Cl-, okay? And you also have sodium hydroxide. You have H+, Cl-, Na+, and OH-, okay? The overall equation is hydrochloric acid plus sodium hydroxide reacts to form sodium chloride plus water. That's acid plus alkali reacts to form salt plus water. Now, what we do is we extract each of the ions from each of these species, because the challenge for us is to represent this in a new way called an ionic equation, okay? So the extraction of all of the ions is given here. H+ is aqueous because all of these are dissolved in water, so it's all aqueous. H+, Cl-. We've also got Na+ plus OH-, because this is now being added to that in the neutralization. So we have 4 ions present. Then we end up with Cl-, Na+, and you've actually got the water that forms from the OH- combining with the H+ from these two species. Now, water is a molecule. For this lesson, you can assume that water is going to form as a molecule, okay? So H2O comes out at the end. Right, so what you notice is that you can actually see that the Cl- don't participate in this reaction. The Cl- do not participate in this reaction. It's just like as if they are just watching from the sidelines and seeing what's going on, because the Cl- don't change. The Na+ don't change either. They just watch from the outside. So this is in direct contrast with what's happening with the H+ and the OH-. You see, these two are combining together to form something that's new. So what we can do is we can actually cross out these, what we call spectator ions, because they're actually doing nothing whatsoever. They're just sitting on the sidelines, just watching. So we can cross them out, and we can actually have a slightly simpler version of what is going on and what is important that's actually happening in this reaction. So this is the most important thing. This is the most important thing. H+ plus OH- going to form water. That's the actual important reaction that's taking place. Nothing is happening to the Na+, nothing is happening to the Cl-. The Na+ and Cl- just hang out. And then, like, once the water forms, if you actually evaporate the water, the Na+ and Cl- will be like, Okay, right, let's just sit next to each other. And then you'll get that ionic lattice that we have studied before. Okay? So this is the ionic equation for the reaction. During neutralization, H plus combines with OH minus ions to form water molecules. When you have an ionic equation, it's important for you to put the state symbols, okay? So aqueous, because that was in an acid, OH minus, that was in an acid, H2O, because we now consider that as being liquid. If you wanted to, you could put H2O aqueous, but that's like saying, oh, we've got water dissolved in water. That don't make sense. So we're going to put H2O, and we're going to say, oh yeah, that's a liquid, all right? Convention. Okay, the next part. Now this is what I touched upon just at the start of that description. This is the second type of neutralization that you can actually have. Here is an acid reacting with a metal oxide. Now this is an insoluble base. Okay, it's an insoluble neutralizer of acids. So that's why it's represented as a solid. Because if you put magnesium oxide in HCl, magnesium oxide is that lovely white ash that you get when you burn magnesium in air. If you try to dissolve that in water, you can't do it. And the HCl, the hydrochloric acid, is in water. So the MgO, the magnesium oxide, will not dissolve in water. That's why we keep it as a solid. But the HCl is soluble in water. We saw it over here, okay? And the reason why it's soluble in water is a question that you may be asking yourself. And the reason why is because the water molecules are actually, in disguise, molecules that have positive parts and negative ends. So they have positive and negative ends. So they pretend to be the opposite charge of any of the ions that you actually have here, and it stabilizes the ions when they're dissolved in water. More on that later on when you cover a topic called covalent bonds. So back over here, so you actually have the H plus ions, which are provided by acids. We have covered that before. So the H plus is attracted to the O2 minus. So the hydrogen ions are attracted to the oxide ions here. They're attracted. And for every one oxide ion, you get two attracted, because this is a plus, and that's a 2 minus. So if a plus joins on with that, it will be OH minus. We've seen that before. So H plus then comes along and latches onto that, and it forms water. Okay, the water molecule just shoots off. The water molecule doesn't have any charge. That's why there's no charge on this. Wait, yeah, no overall charge is what I should say. And what's just watching it from the outside, the bystanders, the spectator ions, Mg2 plus, which used to be hanging out with with O2 minus, and the Cl minus, which was actually in the hydrochloric acid. They just hang out and they think, all right, let's just hang out together then. And for every Cl minus and Cl minus, you have one Mg2 plus that hangs out. So to represent this as an equation, it's more efficient for you to actually talk about what's actually reacting to make something new. 2H plus reacts with O2 minus to form H2O. Okay. So if you then look at the two reactions that we've seen, in both cases you have H plus OH minus reacting to form water. In this reaction over here, you had 2H plus O2 minus, again to form water, liquid water. But look, the O2 minus was as a solid. That's why it's important to put the state symbols when you're doing these equations, okay? And for each of these, you've seen not just one, but two examples where the acid is a proton donor, and where either the OH minus or the O2 minus is a proton acceptor. Now that's an alkali, but an alkali is a soluble base. To make it easy to understand, we can just summarize it as bases being proton acceptors. I saw one question come up and it said, why is oxygen a solid? The reason why it's a solid is because it's an oxide ion that's locked in the lattice. So it's a solid there, okay? Oxygen molecules are a gas, but the oxide ion is part of the solid ionic lattice. No problem, Rashid. Okay. Has that helped? I hope. Has it helped? Quite cool concepts here, and you're really digging into what is actually happening, not just at the atomic level, but like at the ionic level as well. But stick at it, because any concept, any marks that you get on the supplementary section will always be marks that you have above a C grade. Okay. A polite request, please trust that I will send invitations out to the Google Meets on time. Please don't email me at 2:15 this morning, which is what one person did, saying, sir, can you please email me the time for the Google Meet? All right. But thank you very much. I know, it's unbelievable. Rashid's got one question. Please remember to put a question in front of your question. Why is neutralization not a redox reaction? That's a really good question. Let's have a look. This question's got me thinking. Where's my pen? What is actually happening to the H plus and what is actually happening to the OH minus on a deeper level? Here it is. Okay. So, Rashid, just for you, okay? Right. So we've got this reaction that we have just studied. Okay, all right. Now, Rashid, just for you, don't tell anyone, but that process can also take place, okay? That process can also take place, and this is called the dissociation of water. Okay, and this is a really top-level concept that's studied quite extensively at A level. Okay, and we can actually go far enough to say that both of those things can happen at the same time. So much so that as chemists we can consider them to be one and the same, okay? So we use an arrow, a special arrow to show that that can go there, but that can also go there. And what I need to do is I need to shield you from that new information, because it's all classified. And you cannot unlock the understanding of that information there until you do A-level, which I hope you're being inspired to do, because I'm sure if you're asking questions like that, you are an A-level student in the making. So at the moment, you need to concentrate on that and just focus on that. But once you start running, you'll be able to understand that and then combine it together to form that. Okay? Rashid, does that answer your question? So the answer to your question is, we don't consider it a redox reaction because nothing actually will happen to the H plus. It doesn't gain an electron. It doesn't, the OH minus as a whole species doesn't lose an electron because we shroud it with a hood. We put a hoodie on it, H2O, but real chemists know that that can actually go backwards as well. So nothing actually happens, and we interconvert our understanding of that. That's right. Don't tell anyone I told you that. Okay, secret, top A-level chemists only. Right, I hope that answered your question. Right, I shall say goodbye to 9.6, so you can stick your microphones on, 9.6. stick your microphones on and say goodbye.
Goodbye.
Bye-bye. Take care. Stay safe. Wash your hands properly. Yeah, wash your hands properly.
Bye, sir.
Bye. Take care. That was Abhishek. Bye. Make sure you get the back of your palms properly. Bye. Bye, Abhinav.